Okay, thank you very much. Thanks for coming. It's been a long day, I understand. Everyone's tired. I'll try to make this as easy to understand as possible. It's also nice to see some old friends here after such a long time, and most importantly, I would like to thank the organizers for having me here. It's an honor to be here. So what I'll be talking about today is higher AGT correspondences, W algebras, and higher quantum geometric Langlands duality from M-theory. So this is the presentation outline. I'll first give an introduction, and then a lightning review of the 4D AGT correspondence for compact Lie groups that were derived using M-theory in my previous work. And then I'll go on to derive a 5D and 6D AGT correspondence for compact Lie groups. And then we'll talk about the W algebras that we can get from this derivation and how dualities of these W algebras define higher quantum geometric Langlands duality. And then we'll talk about the relationship between the supersymmetric gauge theories that you see on the world volume of the M5 brane, its relationships to the W algebras that it gets in the dual frame. And then we'll talk about a realization of the quantum geometric Langlands correspondence in terms of map between derived categories of D modules and coherent sheaves. And then we'll talk about a higher generalization of the geometric Langlands correspondence as suggested by our results. Higher in the sense that the usual one is in terms of 4D gauge theory. So what happens if we look at something that's coming from 5D gauge theory or 6D gauge theory? So in the language of W algebras, it involves Q-deformed W algebras and elliptic deformed W algebras. And then we'll conclude the talk with some general comments. Okay, so just a little bit of history for 6D, 4D, and 5D AGT correspondences. I'll just be very fast. There's lots of things I want to say, so let me just be quick. So this is just a chronology of all the results of the people who have been working on this, many people, both physicists and mathematicians. Okay, so there are people working on 4D, 5D, and then mathematicians trying to prove the case for 4D in the case of SUN groups. And then what's relevant to our talk today is some previous work that I did in 2013. I gave an M-theoretic derivation of the 4D AGT for arbitrary compact Lie groups, not just SUN, and then its generalizations on ALE spaces and its connections to quantum integrable systems when you add surface operator defects in the world volume. And then in the next sequel to that paper, I gave a derivation of the 5D AGT correspondence and the 6D one, but for SUN only. And then again, with the presence of defects or surface operators, the relationship to higher quantum integrable systems, meaning like, relativistic integrable systems and then elliptic integrable systems. And relevant piece of work by mathematicians in recent times is this work by Braverman, Finkelberg, and Nakajima. So they prove mathematically the AGT for ALE space, ADE groups, simply lace groups. So, and most recently, there were two papers that were also related to the 6D AGT. In particular, they derived the 6D AGT correspondence using string theory. And, sorry, where's the pointer for this one? Is there a pointer? Sorry. Not working. Okay, never mind. It's not working. Yeah. Okay. So they gave a string and field theoretic derivation of the 6D AGT correspondence for SU2, and then in this very recent paper that I wrote just last week, I'll talk about this today. Okay. We'll give a very general generalization of all these results. Okay, like that, okay. That's confusing. Okay, never mind. Okay, so motivations for our work. Okay, so there's a recent work by Kimura and Pestun which showed that you can get these Q-deformed W algebras by studying 5D gauge theories, and these Q-deformed W algebras are what Frankel and Shtikin have studied in the mid-90s or late 90s, which exhibited some kind of Langlands duality, okay? So this is one motivation for this work. This gave me a hint that perhaps we could understand this higher quantum geometric Langlands duality in the framework that I've been studying for the past few years. And the other motivation is that the connection between the gauge theoretic realization of geometric Langlands correspondence by Kapustin and Witten and its original algebraic CFT formulation, that connection is still missing. So we are still trying to figure out where is that connection. So by virtue that you can actually relate supersymmetric gauge theories to W algebras and also take the critical level limits, gave me a hint that perhaps we can all understand this within the same M-theoretic framework that I've been working on. So indeed, this is the case, and I'll explain how this is so to you today. Okay, so in this talk, I will do a few things. Let me summarize. In case you get lost, this is the summary of the talk. So I will present an M-theoretic derivation of a 5D and 6D AGT correspondence for arbitrary compact Lie groups from which we can obtain identities of various W algebras which underlie a geometric Langlands duality and its higher analogues. In this case, when we talk about dualities, we're talking about dualities of algebras, not the correspondence yet. There's a difference. Correspondence, you have objects. In the duality, we're talking about just the W algebra dualities. And once we have that ingredient, we can then go on to elucidate this sought-after connection between the 4D gauge theoretic realization by Kapustin and Witten and the 2D CFT formulation by Berlinson and Drinfeld. The reason is because in Berlinson and Drinfeld's formulation of the geometric Langlands, they make use of this Feigen-Frankel W algebra duality. So now we can connect these two, and that's where we see the connection. Okay, and finally, after that, and second point, we would explain what the higher 5D and 6D analogs of the geometric Langlands correspondence for simply Lie or Kac-Moody groups ought to involve. Okay, and then if we have time, I will demonstrate this result by Nikrasov, Pestun, and Satashvili, a very nice result, which tells you that you can relate the moduli space of 5D and 6D quiver theories to representation theory of quantum or elliptic affine or toroidal G algebras. So, lightning review. So, in the reference 8 and 9, we make use of this set of dual compactifications in M theory. Okay, here. So, with orientifold planes and without, so we can end up getting all the groups, orthogonal groups, symplectic groups, G2 groups, SUN groups, and the B groups. Okay, and so these are dual compactifications on this curve here. Okay, and at the end of the curves, you have defects. These are M9 planes. And so, based on these dual compactifications, we want to compute the BPS spectrum, the space-time quarter BPS spectrum of these compactifications. The space-time quarter BPS spectrum of these space-time compactifications are captured by an index in the world volume. Okay, this was established by Dijkgraaf and Verlinde a long time ago. And this index of the world volume can be captured on one side by a sigma model or instanton moduli space, and on the other side, as you can see here, these are the Tabnat space and the sense manifold, where the asymptotic radius goes to 0. You end up going down to 2A, where there is an I-brane intersection, where you have a chiral WZW model on that I-brane, and when you turn on omega deformation, you actually gauge that WZW model. In gauging that WZW model, you end up doing a Drinfeld-Sokolov reduction. There's a one-to-one match between the field theory, as you can see when you gauge it, and the procedure for Drinfeld-Sokolov reduction in the BRST formulation. Okay, so that's the crux. So on one side of the duality, you end up getting the BPS states, which are counted by these things, which are represented by these things. On the other side, on the intersection brane, as I mentioned in the type 2A frame intersection brane, you actually get a W algebra because you realize the Drinfeld-Sokolov reduction. And the duality of the two compactifications tells you that we have this identity. So this identity is the crux behind the AGT correspondence, because the instanton partition function is summing over these things here, and then on the other side here, I mean, this is the symmetry of the total field theory. Okay, so this is a module. So you're talking about states here, and then these are equivalent cohomology of the moduli space of instantons and Uhlenbeck compactification of that. And so, as you can see, the 4D instanton partition function is given by actually this 5D index, whereby you take the fifth circle to 0. So this 5D index computes the world volume BPS states that we saw, which was spanned by the equivalent cohomology of the moduli space of instantons. Okay, which then means that you can actually write this one here. There is a basis of states here, and you can write it as an inner product of basis of states. a basis of states that can be expanded in this form, the equivalent cohomology here. And from the duality of the equivalent cohomology and the module of the algebra, you can deduce, and the dualities of the frames, that on one side, the instant quantum number is given by the L0 eigenvalue operator, but in the chiral theory, the L0 eigenvalue is the same as the energy eigenvalue, because L0 bar is 0 for chiral theory. Okay, so which means that using the duality, you can also see that this state here is a coherent state with excited energy levels. And so you can recast that, what we wrote earlier on here. Okay, you can recast this as this, whereby this is a coherent state, and this is the AGT correspondence in the pure case. And how do you interpret this? Now, this is something that we see on the other frame, on the C curve, on the I-brane. Okay, this one is on the original frame. And so you notice that to define this thing on the left, the index had to be taken at the limit where beta is 0. Beta is the fifth circle. So on the dual side, this just means that these states are localized to the point where the circle fibration degenerates to 0 size. So you have a sphere, actually. The C curve is actually a sphere that can be seen as an interval with fibration. And the circle fibration goes to 0, and that's where your points are localized. And therefore, these can be interpreted as vertex operators at the poles, okay, with higher order poles. So higher singularities, higher order poles, because they represent conformal dimensions which are greater than 1. Okay, so, and we can actually understand it as this. Okay, so on the I-brane itself, you get these 2 points here. As we mentioned already, these are the states where the states are localized. And on the I-brane itself, there's also an intersecting number of n d6 branes. They came from the Tabnut space, the n-centered Tabnut space. Upon reduction on the I-brane, you get this thing here, this n fold cover of this curve here, which happens to be the Gauss curve. And then in the oriented fold case, because you have an oriented fold, there's a reflection of these number of branes, and you end up getting, 2n of these in there, so 2 case. And so these 2 configurations here can be interpreted in some sense as like the Seibert-Witten curve, okay? And so that was for the pure case. We can, of course, construct the case for the theory with matter. So in the pure case, remember that we started off this way. So we could, of course, consider different configurations that look like that, which through our duality would mean that we would have spheres with different punctures on it, okay? And so using these as building blocks, we can, of course, construct our curve or construct the theory, the quiver theory in this case that we want. So just for ease of illustration, we consider the case of the necklace quiver, because this would be relevant to us. Of course, you can do it for a linear quiver and various quivers, and use different punctures and use different vertex operators to represent the different flavor and mass data. Okay, so you can do this, construct it like that, and eventually what you would get is this. You have a torus, in the case of a necklace quiver, with all these vertex operators being inserted here, and then on the other side, the non-C-brane side, okay, you actually have this theory with all the planes that are representing the vertex operators. Okay, so what's important is this. So if you look at, so this is the case for the AGT correspondence for the case of necklace quiver of NSUN groups, and these are all the primary vertex operators here. So you can compute that they actually are given by this highest weight, of which its conformal dimension is this. So an important point is, if you take the massless limit of the hypermultiplet, okay, take this to be 0, for example, then you realize that its conformal dimension also goes to 0. So the vertex operator becomes of conformal dimension 0, which means it is a holomorphic function, but holomorphic functions on the Riemann surface are just constants. So you have a trivial vertex operator, which also means that your planes also disappear. So it's the case of when you have, well, okay, so sorry. So it's the case of having a hypermultiplet n equals 2 star theory. In the massless case, you get n equals to 4, okay, for torus. Okay, I run out of time, so let me just be very quick. I have 10 minutes left. Okay, let's get to the main stuff now. Okay, so in 5D, you would have the same thing, okay, but the only difference is that in 5 dimensions now, your beta is not 0. You can't take it to 0. So what happens? What happens? Instead of a state that is localized to a point, you have to project that state onto a circle on the I-brain. And once you start to do that, you introduce higher energy excited states. Because a quantum system that is infinitely confined, then the higher modes decouple. But if it takes up a finite space, then you start seeing all these states, excited states coming into the picture, and you end up, and you can compute that actually you get this. Okay, so you get this for the U1 case. And of course, there will be a deformation of the Heisenberg algebra, which looks like this. And the thing is, if you remember our picture just now, we saw an n-fold cover of that diagonal curve. So in the U1 case, there's just one. But in the case of n, you have an n-fold cover, which means that you have a tensor product, an n-tensor product of that theory that we saw. So the n-tensor product, so what happens in the SUN case, it means that you have an n-tensor product of these things here and a vacuum of n-tensor product, still obeying these deformed Heisenberg algebra. And then that tells you that that tells you that the states belong in a level n module of a Ding-Yaohara algebra. That's a mathematical algebra. So through physical derivation, we actually get a result in mathematics which tells us that it must be the Q-deformed W algebra. Okay, I put a Langlands dual here for SUNF because in the simplest case, it is the same. Put it here because in the general case, it will be the Langlands dual. Okay, so this is the case for the SUN. And then we can understand this phenomena as such that the n-fold cover, on each cover itself, you actually have a Yangian theory, okay, of which if there's a oops, how do I, sorry, oops. Okay, so we have a Yangian theory. Okay, so this is how we can understand this from our point of view. So we have a tensor product of Yangians, which end up giving you a W algebra. That is Molik and I think Konikov or Vasarov, I can't remember. Some mathematicians deduced this, and we can see this physically in our picture. And then the Ding-Yaohara algebra is actually a quantum toroidal algebra. So you can see the n-tensor product gives you that too. So these are established mathematical facts which sit in very nicely with our physical picture of having an n-fold cover. Okay, now if you turn off omega deformation on the 2D side, meaning if we take the topological string limits here, okay, if you look at the original compactifications, when you take A3 to be 0, there's no omega deformation on the dual side, because in the dual side, you only see the E3 parameter, okay? And so once you turn that off, there is no omega deformation, meaning that instead of having a W algebra, you actually just get an affine algebra, okay, in this case. And what happens is that instead of getting the Yangian, you just have the usual Heisenberg algebra. Okay, all this is on the 2D side, and instead of the quantum toroidal algebra, you just get a loop affine algebra because you have to project it onto a state which lives on a circle. So if it started out as affine, you have to have a loop. So this is the loop case. And so then what you do next is if you want to get for other groups, you would have to twist it. Meaning there was a circle just now where there was a Zn automorphism. You choose that to be 2, okay, and you twist it, so you end up getting a twisted Heisenberg algebra in this case here, okay, and then same here, you get a twisted loop or toroidal algebra here, and then you turn on omega deformation, it converts it to the Yangian of that Z2 twisted affine algebra and the quantum toroidal of that, and then you end up getting the W algebra that is related to an Z2 twisted SUN algebra, okay, and a Z2 twisted Q deformed algebra. And that Z2 twist of an affine algebra is actually a Langlands dual affine algebra. So you end up getting a Langlands dual algebra. Okay, you end up getting a Langlands dual affine algebra here, okay, right? Okay, so that's why the dual came about. You can do the same thing with the orthogonal case, okay, and get the same thing. Okay, with orthogonal case, so you start with SO2n, then SO2n twist it, you get if it's Z2 twist, then you would get the symplectic case, and then if you 3 twist it, you get the G2 case, okay? So in 6 dimensions, you can do the same, okay? I won't belabor it. Okay, so now, the part where you derive the W algebra, okay, so now let us try to derive the these of W algebras that were formulated by Reshtikin and Franco. To do that, we would need to use the n equals to 4 theory. So to use the n equals to 4 theory, you just have to take the massless limit of the n equals to 2 star theory. And as I mentioned just now, when the mass is 0, the vertex operators become trivial, and so does the plane, and therefore you just end up with this configuration of a torus with no M9 planes. Okay? And so once you have this setup here, which is the same as just now, then remember we had this identity that we already derived. Okay. So if you notice from this compactification, there's a symmetry between the E1 and E2, okay? Because the planes are similar, so you can swap them. So you can swap them, so that's a symmetry. I think this is something that Vasily also mentioned in his work. And so one more thing is that in simply laced cases, okay, the Langlands dual affine algebra is isomorphic to the usual affine algebra, and so it means we can write this. We can write out this identity, the other same. Okay? There's a flip here because this thing here is actually this ratio. So you just flip the ratio, it's just the inverse of the other. This RV is put here formally because in the non-simply laced case, this RV would be this n number that we see later on. But in this case, it's just 1. So what happens if we want to derive it for non-simply laced case? For the non-simply laced case, we need to do a modular transformation of the torus. So we would get a different group. And modular transformation of a torus, in that sense, is just flipping the circles, basically, because the complex structure is given by the radius of one circle divided by the other. If you want to invert it, you just swap the circles. You swap the circles, and you end up getting a different gauge group. But from the point of view of the world volume theory, swapping the circles doesn't do anything, because from the point of view of six-dimensional world volume theory, it's the same thing. Okay? And because of that, we end up getting this identity here. Okay? But mind you, this is in terms of the Langlands dual group. So if you want an identity in terms of the normal group, because our duality is connected to the Langlands dual group, so we end up getting identity of the Langlands dual group. So if we want an identity like what Frankel and Restikin did for the usual groups, we will have to swap the roots and the co-roots of this identity. So in doing that, you convert the Langlands dual group to the group, but you would also have to swap the Coxeter number with the dual Coxeter number, and that's how you eventually get this identity, which is exactly what Feigen and Frankel got in the 4D case. So in the 5D case, if you remember the commutator algebra that we saw for the 5D case had parameters. In other words, we could write the 5D Q-deform algebra in terms of 2 parameters like that. We can parameterize it in terms of 2 parameters. Likewise, you can use the same argument that for the SO2 case, because this is isomorphic to Heisenberg algebra, that it would take a similar form and it can be expressed as a 2-parameter form W algebra. And if you notice that apart from swapping E1 and E2, which is a symmetry of the physical system, changing the orientations of the entire compactification would just swap the sign of the omega deformation. So if you put a minus sign, by swapping the orientation, it's the same thing. So we have a symmetry which is this, okay, of the physical system, which therefore means that if you define this parameter here, PQ over T, it means that P inverse is a symmetry, it's a physical symmetry of the system, which then means that Q swapping with T is a physical symmetry of the system. And then combined with our so what we would have eventually is this. We would have this, but since we are dealing with the simply laced case, we can always write this as the Langlands dual. It's the same thing. Okay, so for simply laced case, only simply laced case, we have this identity here, and this is actually the Q-geometric Langlands duality of W algebras that was defined by Frankel and Restikin in 97. Okay, so the non-simply laced case, what happens? Now, it doesn't work for the non-simply laced case. Why? Because in 5 dimensions, you need to project onto a circle. And there is a preferred circle, which is the S1N, the circle with the twist. So if you swap it, you're actually changing. It's a different theory, so you can't equate them together. So it's a bit more subtle. So there isn't this identity for Q-deformed W algebras beyond simply laced. And so same thing, you can do it for 6 dimensions. In 6 dimensions, if you look at the algebra just now, which I skipped over very quickly, there are 3 parameters inside in the elliptic Ding-Iora algebra, and you can write it as such, and using the same reasoning, we can get a similar looking kind of duality. And so you can see that you can get all these dualities here just by purely physical reasoning. Okay? So all these dualities here, which will be important for us. Okay, so now, the interesting part. How do you see the Langlands correspondence and this W algebra, the connection? So, in the theory, in the world volume theory that we're interested in, okay, the sector that we're interested in is the low energy sector, and that's topological along the R4. Okay, and so this is a strategy that Microsoft and Witten used in their paper. So we replace the plane with a cigar metric, whereby the omega deformation is understood as a rotation of the circle in that cigar. Okay, but at low energies, you don't see the tip of the cigar. At low energies, at far distance, you don't see the tip of the cigar, and it can look just like a cylinder that is rotated. So there are two cylinders here, okay, short cylinders. Short because the excitations are localized near to the tip of the cigar. And so you can see that you end up getting two circles, which make up a torus, each rotated by epsilon 1 and epsilon 2, and then two short intervals here, which represent the axial direction of the cigar. So you end up getting such a configuration. Okay. So you can see that this is a compactification on two toruses, okay, this one and this one. So we are left with a theory that is on I1 cross I2. If you look at it from the perspective of a compactification on this T2, you get an n equals to 4 theory. Okay? The usual n equals to 4 theory that Kapustin and Witten used to actually get geometric Langlands. There are, of course, various twists that we can use, but based on work by S-class theories, that what's living on this curve here, the S curve here, must be a Hitchin system. We know that necessarily the twist that preserves the supersymmetries has got to be the geometric Langlands twist that Kapustin and Witten used. And so because of that, we end up computing the BPS spectrum of that world volume in terms of a sigma model of I1 cross I1. Of course, it is a sigma model with boundaries, and therefore you have branes here, so that's where we represent the branes here. And again, on this side, there's no change. We still get a W algebra on the dual frame. That has no change. So we consider the next configuration whereby you just swap the circles. Okay, same thing. So we swap the circles. And then when you swap the circles, you actually change the gauge group here, right? And once you change the gauge group here, we end up getting the Langlands dual gauge group here. Okay, and then on the other side here, okay, on the other side here, from the duality of the gauge groups being different here, you also get one that is W algebra that's also a Langlands dual of the previous one. And so you can see by swapping, you also swap E1 and E2 because you're swapping the circles. Okay? So you end up getting this. And so eventually you can deduce this picture. You can eventually deduce this picture. So you can see from this picture, there's a S-duality here, okay, which, because the two systems are the same. From a world volume point of view, the two systems are the same because the circles are the same. So you can equate them from here, okay? But this is from the string duality frame, and then you get this one, and then you get this one. Okay, and so eventually we have this picture. So this side here represents what Kapustin and Witten did, but now we are only in for genus 1 torus, we are going to construct the higher one. Okay, and this is the Berlinson and Drinfeld, the crux of Berlinson and Drinfeld's derivation. Okay, so we can construct genus by using our building blocks again, and that will result in the sigma model or the model I1 cross I1 with some BPS equations on a higher genus Riemann surface. And then we know from the work of Kapustin and Witten that this 2D theory that lives on this thing must be a sigma model whose target space is the moduli space of Hitchin's equations on this genus G surface with boundary conditions given by the branes. In this case, it's a distinct coisotropic because we are in a model of complex structure I, and then we have Lagrangian manifold. And as shown by Kapustin in a solo paper, this gives you the derived category of twisted D modules, okay, on the space of GC bundles on sigma G. So what this means is that from our construction, we end up getting this picture here. So you can see. So you have the geometric Langlands duality as understood by Kapustin and Witten, and then you get this one, Fagan and Franco. We're not done yet. So you can take the E1 equals to 0 limit. So if you take the E1 equals to 0 limit, epsilon 1 equals to 0 limit, if you remember that was K plus HV equals epsilon 2 over epsilon 1, if you remember that. So you take that to be 0, you end up getting a W algebra at infinite level. That is a classical W algebra, which you can argue to give you flat LGC bundles through the idea of opus. And since there was a module, you have a module of that, actually. And so here we have this already. And then, so when you take epsilon 1 to 0, in this case here, Okay, so you end up getting this becomes infinity here, okay? And so this becomes the derived category of coherent sheaves on the space of the bundles, which means zero branes, basically. Zero branes, and therefore you have a derived category of flat bundles here. And so this is the complete picture. So eventually you have Kapustin and Witten's picture here. Okay, doing S duality, you get this realization here. And then through string duality, this maps to W algebra modules, which then can be related to flat LGC bundles in this case, and then modules of D modules that are critical. Okay, so then this is the Berlinson and Drinfeld formulation. So you can see that to see this relationship between what Kapustin and Witten did and what Berlinson and Drinfeld did, you just need to use string duality. So only with string duality can you do this. Okay, so I'm out of time. One last thing. Okay, so what about the Haeckel operators and the Wilson operators? Okay, that's something which is an essential ingredient in geometric Langlands. You can use boundary M2 branes to realize them. So all these dots here are boundary M2 branes. Then you perform the string of dualities, you end up getting an M0 brane. Okay, there are M0 branes. So they have been studied before. And these M0 branes, when you reduce to type 2A, they give you the D0 branes. Now they have a whirl line here. So what happens is you have these M2 branes that are on the whirl volume now. You can see that they wrap this genus G curve here. And then they are along the real line of the sigma model. Okay? So they can act as the line operators on the boundaries of the sigma model. But on the other hand, okay, so this is the gauge side. Okay, so where is that? Okay, so you can see that they are like a loop on the I-brane side. Okay, they are a loop on the I-brane side. So you can see that the line on the gauge theory side will give you this action, and then this action. Okay, so there's a correspondence between these two actions. So the line operators on the gauge theory side will correspond to the action of the loop operators on the 2D CFT side on C. Okay, and then likewise for the Wilson line operators. So how do you see that? Okay, so the line operators in gauge theory, what they do is they shift the magnetic flux of the gauge theory. So it takes one object here to another object in this way. So one object that's labeled by this to this. Now on the 2D side, you get a loop operator. That's a monodromy loop operator. Monodromy loop operator that was worked out by Gomez and some Flock. And you can see that actually it maps this partition function to something like this, where there's a shift of the highest weight that labels that partition function. And you can see there's a one-to-one correspondence. The states which are labeled by A are now shifted by A plus H, where just like this thing here, which is related to the Langlands dual representation, H is the weight of the Langlands dual representation of LG. Okay, so you see a one-to-one correspondence. And then the next one for the Wilson loops, they do nothing actually to the zero branes, because the zero branes being point objects. Okay, last one. Okay, so they do nothing. And in the monodromy case, they also do nothing because they just multiply the states by a constant number, so they map it to themselves again. So that's pretty much how you see the connection between Kapustin and Witten's geometric Langlands picture and Berlinson and Drinfeld's 2D CFT formulation of geometric Langlands. Of course, we can continue to define. You can see the slides, they're all here. Okay, so conclusion. Okay. So we furnish purely physical derivations of higher AGT correspondences, W algebra identities, and higher geometric Langlands correspondences. Okay, unfortunately, I didn't have time to finish all that, all within our M-theoretic framework. Okay, we elucidated the connection between the gauge theoretic realization of the Langlands correspondence by Kapustin and Witten and its original algebraic CFT formulation by Berlinson and Drinfeld, also within our M-theoretic framework. So clearly you can see M-theory is a very rich and powerful framework, capable of providing an overarching realization and generalization of cutting-edge mathematics and also mathematical physics. Okay? At the same time, such corroborations with exact results in pure math tells us it serves as an empirical validation of our concepts of string dualities and M-theory, whereby math is the lab. Okay, math is an exact science, so it's a lab. So if they say that A equals to B in math, and we can check that our dualities of our concepts in physics have some manifestation of that result that was derived from a different kind of truth. In that sense, it acts as an empirical validation of our physical theories, and in this case, M-theory. Okay, thank you very much for your time and attention.